Hello everyone and welcome to the recording of the week 21 GV300 lecture. We're going to be carrying on from where we were left off last week, so carrying on with regression, and then we're going to be moving on to multiple regression, which is a topic that we'll be sticking with for the next couple of weeks. So let's get started. So, as I say here, before we get on to multiple regression, we've got one or two things that we need to finish off looking at. And firstly, that's just going to be doing a significance test for the slope coefficient. So our beta coefficient, the gradient of the slope. And this is sort of, we're going to be doing this as follows. So let's set up our test and say, if we want to determine whether a variable is really sort of giving us any information as a predictor, one thing we can do is to look at whether we think the coefficient associated with it, so the gradient associated with it, is 0 or non-zero. Because obviously if it was 0, then we would have a picture that looked like this. So if my beta coefficient was 0, then I would just have an alpha giving me the intercept point where my line meets the y-axis, and I'd have a flat line. It wouldn't matter what value of x you gave me, I'd always return alpha as my answer, because beta essentially is telling me nothing. So we'd like to do a hypothesis test which can tell us whether the beta in our model should be 0 or should be non-zero, which is kind of akin to saying whether the variable should be in or out of the regression that we're producing. So let's have a look at how we do this. We're going to do it by using something called a t-test. In this case, since we've got a small sample for the variable, for the data set that we're working with, because we're carrying on from the example we were using last week with sort of age and education, and the two sort of going into a model against each other. So it may be recalled that when we're looking at a hypothesis test for a mean, we do sort of this. We do sort of x minus the mean and then divide by the standard deviation. And so it shouldn't be sort of too surprising that when we're doing a test for our regression line here, or for our slope coefficient, we're going to do something very similar. We're going to do b, our predictor, minus beta, the sort of the theoretical value that we're trying to compare against, and then divide by the standard error of b. And we don't know what beta is, but our hypothesis is that our null hypothesis is that beta is equal 0, and so we can remove that from the model effectively, and the value we want to calculate to test against is just b over the standard error of b. So if we were to look back at last week's lecture notes, you'd be able to grab the numbers to put in for b and the standard error of b, but I'll save us the effort of doing it and say that there 1.06 was our slope, and we had a standard error of b of 0.136, and when I divide one by the other, I get a value of 7.81 coming out. And as always, then we want to know, does 7.81 put me in the last 5% of the distribution, the last 2.5% of the distribution, the last 1% of the distribution, or nowhere near? And I'm going to make my accept or reject the null hypothesis decision based upon that. So let's have a look at some numbers to test against. So if I was looking at the 0.025 point from a t distribution with 3 degrees of freedom to match up with our data set, then the value I'd get for that would be 3.18. And if h0, we accept h0 if the critical value we calculated is greater than that, and we reject h0 if the critical value is less than that. So we've got a value of 7.81, which is bigger than 3.18, and so we are in the last 2.5% of our distribution. So we're going to reject, and we can have a look at the diagram associated with that, and we can see it's exactly the same thing as we've had before. We've got a value of beta in the middle here, and as I look out towards the edge of my diagram, I'm doing a two-sided test here. So this is the point which is putting 2.5% to the left and 2.5% to 2.5% to the right and 2.5% to the left. The value that I've got of 7.81 is definitely in this extreme 5% of the distribution, and so with 95% certainty we can reject our null hypothesis and say that there should be this value of 1.06 associated with our variable. So that's how one of these tests works. So a standard error test, so when we've got a large sample, so n greater than 30, then the critical value of t 0.025 is roughly 2. So this provides a really quick approximate test for us. So if you're doing one of these calculations and you've got a large n greater than 30, then we just need to look at b over the standard error of b, and if it's bigger than 2, then we can reject at the 5% level. So another way of saying that is that if if b is greater than twice the standard error of b, then we've either got a rare sample or a rare sample with beta equals 0, or in fact beta is not equal to 0. So the next thing we want to look at is confidence intervals associated with this. If we can do a hypothesis test on this value here to determine whether we think it should be 0 or not. But I'd also like to be able to do some confidence interval calculations, because if you gave me a value of xi, say xi is 15, so I'm going to put in a value, say, of x0 equals 15, I can put 15 into here and calculate an associated y value, but I'd like to know with some degree of certainty how likely it is to be that value, or to put a sort of window of sort of certainty around it. So let's have a look at a diagram to explain what I mean by this. We can see here that if I plug the value 15 into this equation, I get 7.06 out, and if I look down at my graph over here, if I take the x value of 15 and look up, then I can read off a y value, a y hat value, and I can then read off the real value associated with 15, assuming that 15 was in my sample set and I had the exact y that matched that 15. What I'd like to do is to be able to look at this line here and say this is the value I observe, but I'm 95% certain that this true value here lies in some window that I can place around that. So I'd like to be able to put some sort of degree of certainty with the calculation, or with the value that I'm saying. So we're going to have a look at how to do this. I'm not going to run through all of the maths in great detail where it all comes from, but I just want to demonstrate that this is something that we do have the ability to do. So if we had a chosen value of x0 and I wanted to put some window around it, then it's going to be what's the expected value of y hat given that x is equal to x0, and I can calculate it by saying a plus b times x0. So this is my linear calculation that we observed on the last page, but then I need to either add or take away. I need to do both so that I get a sort of a value above and a value below. So t of 0.025, so I'm taking the sort of point from my t distribution to put a probability sort of scale along with this, and then I have to multiply that by the standard error of the estimates, and then multiply that by the square root of this sort of ugly looking thing here. And if we go through the calculations, we can see the values that come out the other end. This doesn't look like much fun, but it's something that we can quite easily do. We can go and grab our sort of x0 value, our x bar value. We can look at all the other xi's and x bar. We know what n is. So it's just a case of throwing the numbers into this, and what happens is we get 7.06, which is the value we would expect to get because that's what we calculated on the last page, plus or minus 1.2, just 3 decimal places. So this value here all comes to 1.2. So that gives me a window of plus or minus 1.2 around this point here. And what this expression underneath the square root sign is telling us is it's sort of trying to give some idea of the uncertainty associated with estimating alpha and the uncertainty associated with estimating beta. So it's trying to take account of the uncertainties and then build a window based upon a probability value around that. And we can visualize what this looks like, which is quite nice. So if we were to do the calculation for lots of values of x, then we'd see it gets this shape here, where my line going through the middle here is my predictor line, and then I've got a confidence interval above and a confidence bound below, or sort of error bars, you'll sometimes hear these things called as. And what it's doing is saying if I picked a point here, then I'm, say, 95% certain of being in this gap, and if I pick a point near the middle, then I'm 95% certain of being in this gap, and that gap's smaller. And what this is telling me, or what we can see this is telling me, is as I get towards the edge of my distribution, I've got lots of information to the left, but I've got virtually no information to the right, so I become less and less certain about my predictions. When I'm in the middle of my distribution, I've got a lot of information to the left and a lot of information to the right, so I can be more certain about the value I'm giving you, and consequently we end up with these bars that sort of curve away from our predictor line as they get towards the edge of the data that we have any information about. So that's the kind of shape you could always expect to see. So that ends what I want to say about sort of the standard regression continuing from last week, and we're now going to move on and have a look at multiple regression. So the difference between the standard regression we've been looking at and multiple regression is that we're going to have two or more independent variables. So that's where the multiple part is, sort of multiple independent variables in our model. So here, for example, we've got y equals a plus bx1 just like before, but we've got sort of b1x1, but now we've got a plus b2x2 and an error term on the end. So what are these telling us? B1 is trying to measure the relationship between x1 and y, statistically controlling for x2, and B2 is trying to measure the relationship between x2 and y, controlling for x1. So let's look at how we do this. So if y is income, x1 is education, the information we had before, let's suppose that x2 is equal to age. Then B1 is going to measure the impact on education on income, controlling for any effect age might be having, and we can see how this is done as follows. So what we want to do is isolate the variation in the income, so that's y, that's independent from age, and so I'm going to do this as follows. So y equals a0 plus b1x1 plus v, where v is equal to yi minus y hat, so my observed y minus my predicted y. So clearly what vi is telling me is the variation in income, which is independent from age, since we have sort of removed age as an influence on income here. What we're going to do next is then try and play the same kind of game. This time I'm going to isolate the variation in x1 that's independent of age. So I'm going to say that x1 is equal to a1 plus b1x2 plus u this time, where u is x1i minus x hat. So in this case u1 is the variation in education, not explained by age, since by doing this we're removing age as an influence on education. And then when we want to build our multiple regression model, we do it as follows. We say that y hat is equal to a plus b1x1 plus b2x2, but I can do my b1 calculations as follows. It's going to be v times by u over the sum over v squared, and I'm going to be summing up those things and remembering that v is yi minus y hat and u is x1i minus x hat, and so I can plug all these values into this equation and get a value of b1 out, and I could do similar for b2, and if I had them, b3, b4 and b5. And just as a point of comparison, if we compare what the calculations for b1 were like in a bivariate model, you can see that we're doing something very similar here. You know that this formula here has a sort of very similar form to this formula here. So again, that's kind of reassuring that we're not completely reinventing the wheel here. What we're doing is just an extension of what we were doing before. So we've seen a bit of theory, so let's have a look at an example now, because it's always easier when we can actually sort of plug some numbers in and really get a feel for what's going on. So in our example, y is income, x1 is education, x2 is age, and so I can look at the mean of y, which is 6, I can look at the mean of x1, which is 14, and the mean of x2, which is 30, so I can certainly work out the values that I need from these, and I'm going to plug them all into a sort of bigger table now. And in that table, I'm saying, just to make the sort of table titles easier to read so that the table fits on the page, I'm going to say y is equal to yi minus y bar, x1 is equal to x1i minus x bar, and x2 is equal to x2i minus x bar. So when I say x1 down here, I really mean this value here. So I can work out all of the differences, I can multiply them by each other, and I can sum according to the way the formulas tell me that I need to, and I can then pull all the information that I need to build my model out of that. So it's a bit sort of calculation heavy, so we can once again be glad that SPSS is going to be doing the heavy lifting for us when we do this for real, but let's have a look at how the story goes. So if I want to do this, then my B1 calculation is going to be as follows. I can plug all of those values in it comes out at 0.39. You can check my calculations if you want, but I'm quite happy for you just to trust me rather than running through it all. We can do similar for B2, and when I do it for B2, I get 0.3 coming out as my value, and now that I know those, I can plug those values into my formula to work out what A is, and I can get a value for A as well, and I get a value for A of minus 0.46. So I can now write out my whole multiple regression equation and say that A, it's going to be A plus B1x1 plus B2x2, and I now know what A, B1 and B2 are, and so there's my equation. It's minus 8.46 plus 0.39x1 plus 0.3x2. And if we compare that with the model that we calculated when we didn't have x2 to look at, when we had no information about age, our model looked like this, minus 8.84, so looking sort of very similar to our intercept on our multiple regression model. But if I look at the next value, the coefficient associated with x1, you'll see that I've got 1.06 in the original case, and now I've got 0.39. So that number's gone down a lot. And so what we can see here is the relationship between education and income is now much weaker because we've started to take age into account. So clearly there was more going on there that just having education wasn't telling us. So we can look for multiple regression goodness of fit as well, or goodness of fit in multiple regression model, I should say. We still call it R squared, and its definition hasn't really changed. It's the variation explained by the individual variables this time, divided by the total variation, and we've got a formula that can quite happily do that calculation for us as well. So we can run through some calculations for the example that we've just looked at and compare the multiple regression R squared to the R squared for our original calculation. So here's my table of working for R squared, and I've got to work out the means as well. If I throw all of these values into the formula, the key two ones are this one here, 38.38 and 40. And so my goodness of fit is 38.38 divided by 40, which is 0.96. And remember, sort of R squared sort of runs up to 1 as the biggest it can go, so 0.96 is very good. But our original calculation was good as well, and we've only seen a 1% increase in our predictor variable here, but given that we had sort of 0.95, being able to raise that up anymore is still obviously a good achievement for us. So one problem that you can have when you're working with multiple regression is that not all of your variables have to be in the same, sort of measured in the same units. So in the example we just had, we were quite lucky. We had education, which was measured in years, and age, which was also measured in years. But in most models, that's not going to be necessarily the case, that everything's measured in the same way. We could have had one thing measured in years and one thing measuring, say, an occupational prestige scale going from 1 to 10, where the higher the number, the higher prestige the job is, to see sort of what impact that has on the amount of money that someone's earning. And then we wouldn't have been able to as easily make direct comparisons, because you can't say, 1 year of age is equal to 1 point on the prestige scale. There just isn't a sort of an obvious match-up like that. And so what we need to do is standardize our variables so that we can talk in terms of standard deviation, so that we can compare one thing directly to the other. And we're going to have a look at how we do that. Well, we've seen standardizing variables before when we were doing normal distributions and we were calculating a standard normal distribution. And you can see that very much the same thing is going on here. I'm going to have yi minus y bar, so I'm going to be taking away the mean, and then I want to divide by the standard deviation. And we'll do the same thing for our x's, observations minus mean divided by the standard deviation. And if I do these calculations for all of my xi's, then I can calculate a model, and I can write it down as follows. So I can write down my model as my standardized y is p1 x1 standardized plus p2 x2 standardized, and so on and so on and so on, where the pi's are what we call path coefficients, and they're calculated as follows. We're taking the bi, the gradient coefficient, and then we're modifying it according to the standard deviations of the x's and the y's, to give me a value of, like I say, this path coefficient, or the coefficients going into my sort of standardized regression coefficients model. So once again, let's look at our example of age and income and education and see what the standardized model looks like. So we can calculate the path coefficients sort of in a quite straightforward way. We had all the information that we needed to do it, so that was nice and straightforward, and we can then look at a standardized model, and we can say that y is 0.36 x1 standardized plus 0.63 times x2 standardized, and this gives me a different vocabulary for talking about it, because what I can say is that one standard deviation change in education produces 0.36 of a standard deviation change in income, but by contrast one standard deviation change in age produces a 0.63 of a standard deviation change in income. So another way of interpreting this, interpreting the path coefficients, is to say that P1 is equivalent to the correlation between education and income controlling for age. But it's quite nice that we can just talk in terms of standard deviations, and if I have one standard deviation change in one of my variables, how does that compare with a standard deviation change in some of the other variables that I may have in my model? So it's really just giving us sort of more vocabulary, more language to be able to talk about the model that we're producing. So the next concept that we need to introduce is that of a dummy variable in a model. So this is an independent variable that only has, say, two values, 0 and 1. So it's, for example, measuring a respondent's gender. So we could have a variable x3 that behaved as follows: that people responded 1 if they were female and 0 if they were male, and then we can now quite happily put a variable like this into our regression model to measure the effect of being male or measure the effect of being female on someone's salary. So let's have a look at how our model's going to look now. So note I've taken out x2 to try and keep things a little bit simpler, and replaced it by x3. So we're putting age so we're putting gender in instead of age in my calculations here. And really two things can happen. If the respondent replies 1, i.e. they're female, then my model looks as follows. I have a1 plus b1 x1 plus b3, and the x has gone, it's because it's just a 1 essentially. So I've got a constant appearing in the form of the a, and I've got another constant appearing in the form of b3. If the respondent replies 0, however, that they're male, then my model looks as follows. I have b1 x1, and I have b3 times by 0, and anything times by 0 is going to disappear, so I've got a plus b1 x1, and I'm back in sort of the original case that I was looking at before, where I only seem to have one variable as opposed to two. So in a sense, this variable, or this value b3, is giving me some measure of what it means to be female as far as the model goes. And so if I want to actually do the calculations for this, then I've got my table with the extra value. So let's suppose that I had 2 people who were female and 3 who were male. I can still do all the necessary calculations to work out my regression line, and if I go ahead and do that, it looks as follows. I get I get y is equal to minus 7.37 plus 0.98 x1 minus 0.88 x3, and I can standardize those values as well to get minus 0.90 plus 0.90 and minus 0.15. So you can see that there's a minus sign associated with this. So it's telling me that sort of the effect of being female for this data set is implying that you're earning less than the male counterparts. But the standardized model is giving me some extra information, and it tells me that when I look at this, one standard deviation change in X1 is effectively having 6 times the impact of one standard deviation change in X3, because I've got a 0.90 here and I've got a 0.15 here, so changes here are having more impact than changes over here. So that's all we need to say as far as regression or multiple regression goes for this week. We're going to be carrying on with more of it in next week's lecture. What I think would be a good idea for you to do now is to go and have a go at SPSS. There's the exercises and the solutions are all available for you, so do please take the time to work through those carefully and read through the solutions. I've explained sort of how to interpret everything, so make sure that you understand how to interpret the output of SPSS and that you can create a document similar to the one that I've created, so you could have effectively written up the answers. It is very good practice for the exam that you take the time to practice doing that. And as always, if anyone has any problems or questions or queries, then please take the time to drop me an email and I will respond as quickly as I can. Okay, I will see you all again for next week's online lecture.